One of the relay technician's main tasks is to check and calibrate relays and adjust the settings according to predetermined calculations. In many utility companies, these calculations are performed by a specialist group aided by computer programs. We feel that the relay technician should be aware of how these calculations are performed, along with other factors which must be considered in determining relay settings. Armed with this knowledge, he may sometimes be able to make at least approximate calculations in the field and perhaps identify errors in specification. This factor is particularly important where substation modifications have been carried out and new equipment installed. In earlier tapes in this series, we studied fault characteristics and looked at methods for monitoring system conditions. Please make sure that you are familiar with this material. It may be worth your while reviewing videotapes 3 and 4 once again in order to lay a firm foundation for our current study on fault calculations. In determining the setting of any particular relay, what is it that we need to know? Well, obviously, we must take into consideration any errors that are likely to occur in the measuring devices, that is, the CTs and VTs. We must also make allowance for limitations in the relay itself. However, by far, the most important item is the level of fault current that will be seen by the relay in response to a fault within the protected zone. For certain types of relay, such as directional or impedance relays, it is also necessary to determine the phase angle of the fault current. As we have learned before, the types of fault may be classified as follows: a single phase-to-ground fault, a phase-to-phase fault, a phase-to-phase-to-ground fault, a three-phase fault. Let's take a close look at a three-phase fault. The generator is supplying a 37.8 MVA load at the end of the feeder. The voltage at the load is 21 kV line to neutral, with a current of 600 amps per phase. This current flow produces a small volt drop as it passes through the system, so that the generator internal voltage, or source voltage E, is 22.8 kV. The actual level of current flowing is determined by the total impedance, that is, impedance of the load, about 35 ohms per phase in this case, plus the system impedance between the source and the load. Now let's see what happens if a short circuit occurs across all three phases close to the load. Impedance at the load falls to zero or close to zero, which can be shown as going to ground. The current in the line will now rise to a very high value, limited only by the impedance of the line conductors and the generator winding itself. The line impedance is 1.5 ohms per line, as is the per-phase generator impedance. For simplicity of calculation, let us look at one phase only. As the impedance at the fault is now zero, the total impedance in the circuit is equal to 1.5 ohms in the generator winding plus 1.5 ohms in the conductors. The total current circulating through the circuit now equals 22.8 kV divided by 3 ohms, and this comes to 7,600 amps. The voltage drop along the line is now 7,600 amps multiplied by the line impedance, 1.5 ohms, equals 11.4 kV. So the voltage profile is now as follows: internal source voltage, 22.8 kV. Generator terminal voltage is 11.4 kV. Voltage at the fault, 0. Of course, this very high current flow could not be sustained for long, as it would soon damage the generator windings. Thus, the protection devices would be set to trip the faulty line for this condition. The value of fault current would also be lower if the circuit contained more impedance. For example, suppose we add a 4-ohm reactor in the line. In this case, the total impedance in the single-phase circuit comes to approximately 7 ohms, and the fault current is now reduced to approximately 3,250 amps. From this example, we draw a very important conclusion. In order to calculate the magnitude of fault currents, it is necessary to add all of the impedances in the circuit between the source and the fault. Now, this is not always as easy as the example that we have just seen. For example, look at this system. Here we have several different voltage levels. 23 kV at the generator, 230 kV in the transmission line, and 115 kV in the distribution line. And each of these components of the circuit, the generator, the transformers, the transmission line, and the distribution line, all contain impedance which will contribute to limiting the magnitude of fault current. We cannot simply add the ohmic values of impedances together because they are at different voltage levels. Clearly, the effect of a 10-ohm resistance in a 10,000-volt circuit is much different from that in a 200,000-volt circuit. In fact, the impedance of a transformer appears to be different when viewed from either the high voltage or low voltage side. The ohmic impedance is lower when measured from the low voltage side. The method applied to get around this problem is to express all values as a percentage of a common base. This is known as the per unit system. Now, aren't you glad that you reviewed this subject in videotape number 3? Let's briefly review it once again. In practice, as you know, the value of impedance is usually marked on schematic drawings and on equipment nameplates in terms of percentage. For example, this generator is rated at 220 MVA, and the short circuit impedance is given as 16%. It may be indicated as 0.16 per unit or 16%. This value is related to the circuit impedance at rated load. In this example, the impedance of the generator winding is equal to 16% of the value of total circuit impedance, which places a 220 MVA load on the generator. In other words, a short circuit at the generator terminals has an impedance of only 16% of the 220 MVA impedance. Therefore, the fault MVA and fault current will be much higher than load current. The fault MVA equals 220 MVA divided by 0.16 equals 1,375 MVA. This example shows us another very important point. Percentage impedance must always be related to a certain MVA capacity. And in order to add the impedances, they must all, of course, refer to the same base MVA. Knowing this, let us continue with our example. We see that as well as different voltage levels, each of the percentage impedances are related to a different base MVA. 220 MVA on the generator, 250 MVA on this transformer, 250 MVA on this line, 46 MVA on this transformer, and 100 MVA on this line. So we must first convert all of these impedances to the same base MVA, and we will arbitrarily select 100 MVA as the base. In order to convert the generator impedance value to 100 MVA, we simply divide 0.16 by 220 and multiply by 100. This comes out to an impedance of 7.3% on a base of 100 MVA. Continuing on through this circuit, we come up with percentage impedance values for each component. Adding these gives us a total impedance of 49.4% or 0.494 per unit on a base of 100 MVA. This means that a fault close to the load would be fed by a fault capacity of 100 MVA divided by 0.494 equals 202.4 MVA. A fault close to bus A would be fed by a fault capacity of 100 MVA divided by 0.097 equals 1031 MVA. But what does this mean in terms of current as measured by CTs in the 230 kV line? Remember, three-phase MVA equals √3 times line current times line-to-line voltage. In each phase, the CT would measure line current, that is 1,031 MVA over 230 kV times 1.732 equals 2,588 amps. When using the per unit system, remember the following points. MVA refers to three-phase MVA. Voltage refers to line-to-line voltage. Impedance refers to per phase to neutral. Please switch off the tape now and review this material in your workbook. In our previous example in the last segment, we added all of the percent impedances together in order to find the total system percentage impedance related to a specific MVA base. However, it is not truly accurate to arithmetically add these impedance values, as each item is probably at a different phase angle. This is caused by the different ratio between ohmic resistance R and inductive reactance X in each element of the circuit. The actual impedance diagram would probably look something like this. You can see that by adding the impedance values arithmetically, the resultant would actually be greater than the true value. This in turn would give us a lower value of fault capacity and consequently fault current. So to be truly accurate, we need to add these values vectorially. This could be done graphically, or it can be calculated by the following method. The impedance of this line is stated to be 10 ohms at a phase angle of 60 degrees. If we draw this accurately, we find that the impedance is made up of ohmic resistance 5 ohms and inductive reactance 8.6 ohms. We can check this from our trigonometry table. The cosine of 60 degrees is 0.5. The sine of 60 degrees is 0.86. Once we know the components of an impedance, it may be written down like this. Z, impedance equals 5 ohms plus J, 8.6. The operator J indicates that this quantity is displaced from the resistance by an angle of 90 degrees counterclockwise. For a quantity which is clockwise by 90 degrees, the J would have a minus value. So if we now have a circuit like this, composed of several elements, each indicated as R plus JX, we can add the resistances, R, and inductive reactances, JX, separately. The resultant sum comes to 8 ohms resistance plus 24 ohms inductive reactance, and this gives us a total impedance of 25.3 ohms. If we wish to convert this to per unit impedance, we would have to select a base MVA, say 100 MVA, and apply the system line voltage, 33 kV in this example. This is satisfactory because the transformer impedance was measured from the high voltage side. The per unit impedance is given by the expression per unit Z equals base MVA divided by kV squared times ohmic impedance Z. In our example, this equals 100 MVA divided by 33 squared times 25.3 equals 2.32 per unit, or 232%. Just as the ohmic values of impedance need to be added vectorially, so must the per unit values. To help with this calculation, the percentage values are also broken down into in-phase and 90-degree J components. In this example, all of the per unit impedances are calculated on a base of 100 MVA. Note that the generator impedance is given a value of J 13.33%. This is all reactance, as the conductors are considered to contain negligible resistance. Similarly, the transformers are given reactive values only. The underground feeders and overhead line are both given resistive and reactive values. All of the respective R and X values must be added together. But note here we have a parallel circuit. Thus, in order to calculate the total impedance, we find it helps to draw an equivalent circuit. This is especially worthwhile when the system configuration is more complicated. In this simple example, we replace the parallel circuit with a single impedance and indicate the equivalent value. Now, adding all of the impedances together, we come up with a percentage impedance of 27.6 plus J, 103.6.9% on a base of 100 MVA. By calculating this out, we find that the total impedance is equal to 1037.25%. From this, we can calculate that for a fault on the 415-volt bus, the fault MVA will be 100 MVA divided by 10.37, and this comes out to 9.641 MVA. And to obtain fault current, we need to divide the fault MVA by √3 times the bus voltage. This comes out to 9.641 MVA over 1.732 times 415 equals 13,412.6 amps. Now, let's see what happens to our calculation if we use only the reactances in the circuit, as after all, they are predominant. The total per unit reactance, that is, all the J values, add up to 1,036.9%. From this, the fault MVA comes out to 9.644 MVA, and the fault current is equal to 13,417.1 amps at the 415-volt bus. This value of fault current exists in all three lines, as it is a three-phase fault. Clearly, by using the reactance only, there is very little difference in the answer. Also note that the error provides a slight overvalue, which in relay calculation is probably preferable to an undervalue. For this reason, it's very common in carrying out fault calculations to utilize the reactance values only. This is especially so when generators and transformers are included in the system. So up to now, we've seen that it is fairly simple to calculate the impedance values and corresponding fault values for a radial circuit. However, in practice, as we know, networks are considerably more complicated and often consist of several closed ring systems like this. In order to study this system, the first thing we need to do is draw the equivalent circuit, calculate equivalent impedances, and then step by step simplify as far as possible. The first stage looks like this, and for this example, we are leaving out the numerical values and indicating Z for different elements of the circuit. ZG here represents the generator impedance, and here are the two transformers, each with impedance ZT. The overhead line between them, that is line C, is shown here, with impedance ZC. Lines A and B, that is ZA and ZB, are connected into the faulted bus. In fact, these three overhead lines, ZA, ZB, and ZC, form a delta connection. It has been found from experience that the delta arrangement cannot easily be reduced for calculation. Instead, we can substitute a Y connection section and adjust the Z values accordingly. The imaginary Y circuit is connected like this. The equivalent impedances ZCA and ZAB are connected to the same terminals as the original impedance ZA. In order to find substitute values, we use the following expression. ZAB equals ZA times ZB over ZA plus ZB plus ZC, and so on for the other legs. If you want to find out how we arrived at this expression, please check in your workbook, where a more detailed explanation is given. Now, having substituted the delta circuit, we can continue to simplify this equivalent circuit. We now have the generator impedance ZG, a parallel circuit representing the two branches, with each one including a transformer ZT and the line impedance. Finally, we have the substituted impedance ZAB. We can now go a stage further by inserting one impedance in series to substitute for the parallel circuit. And finally, all of the impedances are added to allow us to calculate the fault capacity. I'm sure that you can already see why computers are used to assist in calculation of fault values. But for now, it's time for a break. Please switch off the videotape and review this material in your workbook. In this segment, we're going to look at the application of symmetrical components, a tool to help us analyze unbalanced fault conditions. In the previous segment, we analyzed the conditions for a three-phase fault. The conditions before the occurrence of the fault are represented by this phasor diagram here. The three equal phase to neutral voltages are shown, and by convention, they rotate in the counterclockwise direction in the sequence A, B, C. Although this is the conventional sequence of phase rotation, be aware that some power systems are connected to operate with the opposite phase rotation sequence, that is A, C, B. Keep a lookout for this item on drawings and schematics, especially when working with neighboring utilities. The symbol E is often used to indicate generator internal voltage. E is, in fact, the source voltage behind the generator impedance. When the short circuit occurs across all three phases, the voltage at the fault falls rapidly. But note, all three phases are still of equal magnitude, and the three phases still maintain the same relative angular displacement, that is, 120 degrees apart. These fault voltages are indicated by the letters VA, VB, and VC. The current rises dramatically, and its angle of lag has now increased to 60 degrees. This is an approximate value which is dependent upon the ratio of inductance to resistance in the impedance to the fault. It is important to note that the current phasors are still balanced. That is, they are all of the same magnitude and are displaced 120 degrees apart. So even though the current has increased and the voltage decreased due to the fault, the system still remains in balance. That is, the three phases are symmetrical. This is convenient, as it enables us to look at one phase only when carrying out our fault analysis, as we did in the last segment. This balanced condition is known as the positive sequence, and it is identified by the symbol 1. Clearly, the positive sequence voltages VA1, VB1, and VC1 at the fault will be lower in magnitude than the source voltage E due to the greatly increased current flow and consequent increased voltage drop. Now, when the fault is unbalanced, say a phase-to-phase short circuit, it is not so easy to analyze. For study purposes, the short circuit is considered to have zero impedance. This phasor diagram shows just how unbalanced the system becomes under these conditions. Due to the unbalance and change in impedance, the voltages on lines A and B have come together because of the short circuit. This condition is brought about by a combination of the balanced positive sequence voltages from the generator and the balanced negative sequence voltages which are generated at the fault. The negative sequence phasors use the subscript 2 for identification. As its name implies, the negative sequence voltages rotate in the sequence ACB instead of ABC. The magnitude of voltage in each phase is the same. Both positive and negative sequence voltages are present during the fault condition, so we can superimpose the phasors like this to produce the resultant condition during the fault. You will remember that we discussed the subject of symmetrical components in tape number 4 in this series. The voltage between lines A and B, that is VAB, is now 0, as the fault impedance is 0. Consequently, the value of VA is the same as VB. VA and VB represent phase voltage to neutral. VA equals VA1 plus VA2. Similarly, VB equals VB1 plus VB2. These positive and negative sequence values must be added vectorially, of course. Note that the magnitude of positive and negative sequence components is the same. VA1 has the same value as VA2, but their phase angles are different. Also, inspection shows that for this fault condition, the magnitude of voltage VA equals VB equals VA1 equals VA2. The phase voltage in the unfaulted line VC equals VC1 plus VC2. And as they are in phase and of equal value, the magnitude VC equals 2, VC1 equals 2, VC2. Here we see the current phasors for this phase-to-phase fault. Note that positive sequence current phasors are in phase with positive sequence voltages. By contrast, negative sequence currents are in the opposite direction to negative sequence voltages. I1 and I2 are equal in magnitude. Adding positive and negative sequence current phasors shows us that the current in the faulted lines A and B has a magnitude equal to √3 times the I1 current. The actual values of VA1, VB1, etc. are calculated by taking into consideration the source voltage E and the voltage drop caused by current flow through the impedance to the fault. And we'll look at this in the next segment. So much for a phase-to-phase fault. When there is a ground fault present, we have yet another symmetrical component to deal with. This is known as the zero sequence component because there is no phase angle difference between each phasor. For identification, it is given the subscript 0. In each of the lines, the zero sequence component is at the same phase angle and has the same magnitude. By superimposing the positive, negative, and zero sequence components together, we can derive the phasor representation for this ground fault condition. First, we see that the voltage on line A falls to 0 or close to 0, depending upon the value of fault resistance. We already know from experience that this happens on a ground fault. On the other two lines, adding positive, negative, and zero sequence components gives the phase voltages VB and VC at the fault. We have been looking at voltage components here, but the same concept applies to current as well. Here we see the phasor diagram for current in the ground fault, broken down into symmetrical components. As before, the positive sequence currents are produced at the generator and the negative and zero sequence currents at the fault. By superimposing the diagrams, that is, adding the components vectorially, we can determine the relative values of current flowing in different parts of the circuit. For example, the current in phase A, IA, is equal to IA1 plus IA2 plus IA0. We see from the diagram that all of these components are acting in the same direction, giving rise to a very high value of current. Now, let us look at the current in phase B. By adding IB1, IB2, and IB0, the resultant IB equals 0. Similarly, IC equals 0. The magnitude of each component is of equal value, that is, IA1 equals IA2 equals IA0. Therefore, the magnitude of fault current IF equals IA equals 3I0. This does not mean to say that the zero sequence currents IA0, IB0, and IC0 are all acting together in the faulted phase A. But the magnitude of IA1 and IA2 is equal to IA0, and this is a convenient method of calculation, as we shall see. The main points to remember when dealing with symmetrical components are: 1. Positive sequence components are of equal magnitude and rotate with the sequence ABC. The phase voltages are displaced equally by 120 degrees. 2. Negative sequence components rotate with the sequence ACB. As before, the magnitude in each phase is identical, and the phases are 120 degrees apart. 3. Zero sequence components are also of equal magnitude, but rotate in phase. The phasors are fixed in relation to the others. 4. When calculating symmetrical components, load current on the line is usually considered as zero because the load impedance is too high, relatively, to have any effect. 5. In any particular phase, the value of current or voltage is the sum of positive, negative, and zero sequence components. For example, VA equals VA1 plus VA2 plus VA0, and IA equals IA1 plus IA2 plus IA0. 6. In a phase-to-phase fault, no zero sequence components are present. The unfaulted phase voltage is equal to 2V1. V1 equals V2. The faulted phase voltage is equal to V1. IF equals root 3 times I1. 7. In a phase-to-ground fault, the total current into the fault equals 3I0. I0 equals I1 equals I2. And 8. When dealing with symmetrical components, values always represent phase-to-ground conditions. Included in your workbook is a table of standard diagrams showing symmetrical voltage and current phasors for different fault conditions. Take time to study this and take particular note of the relative magnitude of phasors for different fault conditions. In performing fault analysis for unbalanced fault conditions, the major task is in calculating the values of symmetrical components in terms of both magnitude and phase angle. We're also faced with the problem of adding together quantities that are acting at different phase angles relative to each other. The computer cannot look at phasor diagrams as we can. Therefore, some means of identifying phase angles must be provided to help calculate these values. In the last segment, we looked at the application of operator J for identifying quantities with a 90-degree displacement. In studying symmetrical components, the operator A is used to indicate a phasor displacement of 120 degrees in the counterclockwise direction. For example, look at this phasor representation of positive sequence currents. It shows the balanced current in each phase A, B, and C, with the subscript 1 indicating positive sequence. The current IC1 is equal in magnitude to IA1, and its position is indicated by the operator A, that is 120 degrees counterclockwise to IA1. IB1 is of the same magnitude as IA1, and it is located at 240 degrees counterclockwise. Therefore, it is preceded by the operator A squared. So without using a diagram, the relative positions can still be identified and calculations performed. Here is the same notation for the negative sequence system and the zero sequence system here. In order to simplify calculations for the computer, the different values are written in terms of a common phasor, say A1, using the A operator. For example, IB equals IB1 plus IB2 plus IB0 may be written IB equals A squared IA1 plus AIA2 plus IA0. Similarly, IC equals AIA1 plus A squared IA2 plus IA0. But how can we add these numbers together that contain the vectorial symbol A? Well, they must all be referenced to a common point, 0 degrees, conventionally shown like this. On this diagram, let us say the base value is 10 at 0 degrees. Now, if we rotate this quantity 120 degrees anti-clockwise, we call it A10. This can be resolved in terms of the reference angle 0 plus J quantities. A10 is equal to minus 5 plus J 8.6. The cosine of 120 degrees equals minus 0.5, and the sine equals plus 0.86. the A squared indicator at 240 degrees is equal to -5 minus J 8.6. Now we can add the horizontal and vertical quantities separately. Keep an eye open for this operator A when examining printouts of symmetrical components. From the point of view of the technician working in the field, we can come up with reasonably accurate fault calculations without getting too complex. And we'll be talking about this in the next segment. For now, please switch off the tape and review this material in your workbook. We already know that in order to determine the value of fault current, we need to divide the voltage E by the circuit impedance between the source and the fault. E refers to rated source voltage, as this is the voltage which is acting at the instant of the fault. The impedance to the fault is determined by adding the values of impedance of all of the elements in the circuit, not forgetting to allow for any change in the voltage levels. We did this in earlier examples in this tape. Where symmetrical components are being used, we need to take into account the positive, negative, and zero sequence impedances. Let's see what we mean by this. With a three-phase fault, the balanced condition consists of positive sequence voltage and current only. The positive sequence values represent conditions at the fault. The voltage drop between EA and VA1 equals IA1 times Z1. The positive sequence voltage drop is a function of the positive sequence current and positive sequence impedance. Phase values of voltage, current, and impedance are used throughout these studies. For a single line-to-ground fault where positive, negative, and zero sequence components are present, we need to allow for volt drop in all three networks. On the faulted line, we consider the fault voltage to be zero. Therefore, EA equals the total voltage drop in phase A equals IA1Z1 plus IA2Z2 plus IA0Z0. But we have already discovered that IA1 equals IA2 equals IA0 or I0. Our impedance diagram now looks like this. EA equals I0 times Z1 plus Z2 plus Z0. Once we know the value of total impedance for each sequence from source to the fault, we can calculate the value of I0 by dividing EA by the total of all the impedance values. We also learned earlier that the fault current IF equals 3I0. Actually, the different elements of a circuit do not always present the same value of positive, negative, and zero impedance. For example, on a transmission line, we find that the impedance offered to the flow of zero sequence current may be about 3 times that of positive sequence impedance. In this case, Z0 equals 3 times Z1. However, the negative sequence impedance is the same as the positive sequence impedance. Z1 equals Z2. For a transformer, all three impedances are equal. That is, Z1 equals Z2 equals Z0. For a generator or other rotating synchronous source, such as a synchronous condenser, Z1, Z2, and Z0 may all be different. These values are usually indicated on the relevant drawings and specifications. Let's look at a phase-to-phase fault. In this case, we only have to consider positive and negative components. Considering the voltage between line A and line B at the fault to be 0, we can say that EA equals the total voltage drop equals I1Z1 plus I2Z2. We have already learned that under these conditions, I1 is equal to I2 in magnitude. Therefore, EA equals I1 times Z1 plus Z2. So the value of I1 is equal to EA divided by Z1 plus Z2. Fault current IF equals √3 times I1, as we saw previously. And EA equals E line divided by √3. So by substituting IF divided by √3 for I1 and E line divided by √3 for EA, we can see that the √3's cancel out, and we have an important relationship. Fault current IF equals the line voltage EL divided by Z1 plus Z2. In this system, we have a 75 MVA generator which is supplying several 11 kV loads. This 15 MVA transformer supplies a 33 kV bus. At the other end of the 33 kV feeder is a 10 MVA transformer which supplies the load bus at 11 kV. All of these voltages refer to line. First, let's look at a fault occurring on the 33 kV bus. The fault consists of a short circuit between phases B and C. This is a phase-to-phase unbalanced fault. In order to calculate the value of fault current, we will need to take into consideration the impedance values for the generator and transformer. For the generator, the value of Z1, Z2, and Z0 are all indicated on the drawing, both in percentage values and ohmic values also. Note that as J values only are given, the reactance values alone are being considered. Note also that the ohmic values are given for 11 kV and also the equivalent for 33 kV. This is necessary because the fault, in fact, occurs on the 33 kV bus. Also noted on the drawing are impedance values for the transformer, and this is the same value for Z1, Z2, and Z0. As this is a phase-to-phase fault, there is no ground current, so there is no zero sequence component. And as the fault is on the 33 kV bus, we only have to deal with those positive and negative sequence impedances. The total positive sequence impedance between the source and the fault on the 33 kV bus is equal to the generator Z1 plus the transformer Z1. That is J 2.54 plus J 7.26 equals J 9.8 ohms at 33 kV. The total negative sequence impedance to the fault is equal to the generator Z2 plus the transformer Z2, which is the same as transformer Z1. Total Z2 equals J 1.96 plus J 7.26 equals J 9.22 ohms at 33 kV. The fault current IF equals the line voltage E line divided by Z1 plus Z2. Recall there were √3s in both the original fault current and voltage formulas, but they canceled. The total fault current then is equal to 33 kV divided by Z1 plus Z2 equals 33 kV divided by J 9.8 plus J 9.22. And this comes out to 1,735 amps. This is the value of fault current flowing in the line IB and IC. This current lags voltage EBC by 90 degrees as the impedance is considered to be all reactive. But what is the effect of this fault current on the generator, which is supplying the 11 kV side of the transformer? Here we see the transformer Y connected at 33 kV and delta connected on the primary side at 11 kV. Load current is considered zero, so there is no current in A-phase transformer secondary. This means there is no current flowing in the transformer's A-phase primary winding. In phase B, we have 1,735 amps flowing to feed the fault, and this current returns through phase C. Applying the voltage transformation ratio as shown here, we find that there are 3,005 amps flowing in both primary windings in the direction shown. See your workbook for more details. So we have the generator supplying 3,005 amps to phase A, which bypasses primary winding A and enters C at the delta connection. The generator supplies 3,005 amps to phase B, and the total, 6,010 amps, returns to the generator along line C. Our protection at the 33 kV bus and at the generator would need to be set up to take into account these values. Now let's look at the example of a ground fault occurring on phase C at the generator bus. The value of zero sequence current I0 will be equal to EC, that is 11 kV over 1.732, divided by the impedance Z1 plus Z2 plus Z0. From the ohmic values indicated on our drawing for 11 kV, this total impedance comes to J.28 ohms plus J.218 ohms plus J.107 ohms. That equals J.605 ohms. I0 equals 6.35 kV divided by 0.605 equals 10,500 amps. But fault current, IF, equals 3I0. In our example, this comes to 31,500 amps. And what would be the relative phase displacement of this current? Well, as all of the impedance values given are J values, the fault current would be lagging by 90 degrees on phase voltage EC. Now, let's look at a more complicated phase to ground fault, this time on phase C of the 11 kV load bus. The neutral point of the 11 kV bus is solidly grounded at the transformer secondary. Thus, in calculating fault current, we need to take into account the zero sequence current at this point. However, zero sequence current will not flow in the generator or in the 33 kV line because of the delta Y transformers. There is no ground path. The zero sequence current simply circulates in the delta winding. So in order to calculate the fault current, we need to take into consideration the total positive sequence impedance Z1 for the generator, the 15 MVA transformer, the line, and the 10 MVA transformer. We also require the negative sequence impedance for the same elements. And note that except for the generator, these values are the same as for positive sequence impedance. We also have to add the zero sequence impedance for the 10 MVA transformer, and this also is the same value as the positive sequence impedance of that transformer. Our impedance diagram looks like this. We have Z1 and Z2 for the generator, Z1 and Z2 for the supply transformer, 3 times Z1 for the load transformer, and 2 times Z1 for the line. Putting in the numerical values for 11 kV from our diagram, we find that the total impedance, R plus JX, comes to 0.334 plus J 6.568 ohms. Clearly, the resistive component, which is part of the line impedance, is exceedingly small, and in this example can be ignored. Thus, we can calculate that the zero sequence current in the grounded phase, IC0, equals 11 kV over 1.732 divided by J 6.568 ohms equals 967 amps. Fault current equals 3 times I0 equals 2,900 amps. In many systems, the value of fault current is limited by placing a resistor in the neutral grounding connection. Let us see the effect of placing a 12-ohm resistor in the 11 kV neutral. This resistance acts in all 3 of the positive, negative, and zero sequence circuits. Therefore, the value 3R, that is 36 ohms, must be added to our impedance diagram. Now, the total impedance comes to 36.334 resistive ohms plus J 6.568 reactive ohms. The total impedance is now 37.35 ohms. I0 is now limited to 11 kV over 1.732 divided by 37.35 equals 170 amps. Fault current equals 3 times 170 equals 510 amps. Now, obviously, this subject of symmetrical components is quite complex, and we have only taken a brief look at it here. Relay technicians would not normally have the time nor the required impedance data for this, but you will now have an understanding of what the fault engineer is doing and some of the problems he is faced with. For now, let's take a break, and then we'll come back and look at the setting of relays. Please switch off the tape and review this material in your workbook. Having determined the anticipated level of fault current for different conditions, we should be able to set up our relays to protect the circuits. The pickup setting of the relay depends mainly upon the limits of the equipment being protected. We also need to know the anticipated level of fault current for different types of fault at different locations. But there are many other considerations. Where is the relay located in relation to the fault? What errors are introduced by the measuring circuit, CTs and VTs? Are delta Y voltage transformations correctly allowed for in both the primary circuit and the measuring circuit? This factor may affect distribution of fault current. In this arrangement shown here, CTs are located on each 66 kV feeder as it leaves the generator bus, and protection relays are located nearby. Typically, the feeder will have a CT in each phase. The CT secondaries are Y-connected, and each leg is connected to an overcurrent relay. On this radial circuit, these relays are set to protect against phase faults downstream of the CTs, that is, a phase-to-phase or a three-phase fault. We are using 66 kV for purposes of example. Your system may have 69 kV or other voltage standards. But look, this particular feeder supplies, through a transformer, an 11 kV bus at the load end. If we need these overcurrent relays to protect for faults on the 11 kV system, we must obviously allow for the voltage transformation. That is because a fault current on the 11 kV system will be represented by a lower value on the 66 kV feeder. For example, a 10,000 amp three-phase fault on an 11 kV feeder would be seen by the 66 kV CTs as 10,000 divided by 6 equals 1,666 amps. For a typical CT ratio of 400 to 5, the value of secondary current passing through each phase relay would be just over 20 amps. Now let's look at the situation if the bus fault had been phase to phase only, say phase B to phase C. Calculation, backed up by experience, shows that the magnitude of fault current will be less than that for a three-phase fault at the same location. In fact, there is a distinct relationship. Assuming that the positive and negative sequence impedances are the same throughout the system, the value of fault current for a phase-to-phase fault is equal to 0.866 times the value for a three-phase fault. In our example, this produces a fault current of 8,660 amps in phases B and C. The current flowing in phase A is considered to be zero, as under these conditions any load current is relatively negligible. On the high voltage side of the transformer, we have zero current in winding A and a current of 833 amps in each of the windings B and C. This is determined by applying the voltage ratio in each phase. Studying the direction of flow for the 66 kV delta winding, we see that the current in line A is 833 amps. In line B, it is 833 amps, and in line C, 1,666 amps. This is interesting. It means that the overcurrent relay on phase C will measure the same current value as for a three-phase fault at the same location. For most types of protection scheme, a fault detected on any one phase results in the tripping of all three phases. So we can safely say that in this configuration, if all the relays in all three phases are set up to protect against a three-phase fault, they will also protect for a phase-to-phase fault. In many systems, each 11 kV feeder is provided with its own protection relays located at the 11 kV bus. In this case, it would be essential to coordinate the setting of the 66 kV feeder protection with that on the 11 kV feeder. The settings should be graded so that the 66 kV protection allows at least a 0.5 second operation margin in order to allow the 11 kV protection to operate first. You will remember that we discussed this item in our earlier videotape on relay coordination. So far, we've been considering phase faults only. For ground faults, the usual method is to measure the value of zero sequence component I0 or V0. Remember, if there is no ground fault present in the circuit, then there are no zero sequence components. Where a ground fault is present, then the value of fault current IF is equal to 3 times I0. Here is a very common connection for measuring zero sequence current. The ground fault relay, in fact, measures the residual current from the three phases. If all three phases are perfectly balanced, then there will be no residual current. When a ground fault does exist, the ground relay will measure the total out-of-balance residual current, and this is equal to 3 times I0. So let's look at the case of a ground fault on phase C of the 66 kV line. The fault occurs at the far end, and the fault current flowing is limited to 400 amps by this neutral grounding resistor. As before, we consider no current flow in the unfaulted lines. The value of secondary current presented to the overcurrent relay in line C is equal to 400 amps times the CT ratio 5/400 equals 5 amps. Now, this is a much lower value than the three-phase fault that we examined earlier. So it is likely that the overcurrent relay could not be set to protect for both conditions. This is the reason for the ground fault relay, which measures the residual current, in this case 5 amps. The ground fault relays are always set to a much lower value than the phase overcurrent relays. Because of this relatively low setting, ground fault relays of the electromagnetic type are likely to experience a greater margin of error. This must be allowed for when determining the relay settings. All right, in this final segment, we have tried to show you that there are other considerations involved in determining relay settings over and above the calculations of fault currents. If you want to get more information on these matters, talk to your supervisor. And also take the time to study the instruction manuals that support your protection equipment. Please switch off the tape now and thoroughly review this material in your workbook.